Welcome to Implexis, the 23rd edition of the International Symposium on Physics. We ask all participants to keep the microphone off during the entire session to avoid interruptions. For our Zoom audience, in case of any inconvenience that may arise during the session, we ask that you send a direct message to the staff, who have the name Implexis staff in this session. If you would like to ask Dr. Natelson a question, please send it as a direct message to Implexis Q&A. For those of you who are attending in person at the Congress Center, you can send your questions to him through our staff. Today, we are joined by Douglas Natelson. Douglas Natelson graduated summa cum laude from Princeton University in 1993 with a BSc in Mechanical and Aerospace Engineering and a certificate in Engineering Physics. On a Hertz Fellowship, he went on to study experimental low temperature condensed matter physics at Stanford University with Douglas Osheroff. After receiving his PhD in 1988, Professor Natelson spent 2 years as a postdoctoral member of technical staff at Bell Laboratories, formerly known as Lucent Technologies, in Murray Hill, New Jersey. He joined the faculty of the Physics and Astronomy Department at Rice in the fall of 2000 and became a fellow of the Rice Quantum Institute. Professor Natelson received a courtesy appointment in electrical and computer engineering in fall of 2001. He was promoted to associate professor in spring of 2006 and full professor in spring of 2010. He became a courtesy appointee of Rice Department of Material Science and Nanoengineering with its inception in 2013. Professor Natelson has been chair of physics and astronomy since July 2016. Welcome, Dr. Natelson.
Thank you very much. It's my pleasure to virtually be here. I'm sorry I couldn't attend in person, and I really want to thank the organizers for giving me the chance to talk to you and to present some of our work. I guess I should share my screen now.
Yeah, sure.
Okay, so hopefully this is the correct screen to share. Are you seeing the correct view?
Yes.
Great. Okay. Well, I guess I will get going. Again, thank you very much for having me. I'm going to talk today about noise and electrical noise specifically, and how we can use noise as a tool to understand some pretty exotic physics that happens when electrons in a solid stop acting like electrons, but like individual electrons. And I'll try and give enough of an introduction so you can see what I mean by that. I should say, of course, I always like to start with the acknowledgements. That way, even if I run out of time, I'm able to properly acknowledge the people who really contributed to the work. I'm going to talk about a couple of scientific results once we get rid of some introductory material, get through some introductory material. And the first set of results is about electrons in superconductors, in copper oxide high temperature superconductors specifically. And the senior student on that work was Pan Zhou. He was really absolutely fantastic and did some very, very challenging things. And the samples came from the group of Professor Bozovich, who is at Brookhaven National Lab in New York. And we really couldn't have done the work without the samples, as you'll see later when I talk about it. The second set of work I'm going to talk about, where the electrons really don't act like electrons anymore, apparently, is work done by Pan's successor, Liang Chen. And we've just submitted this for publication, and it's out for review right now. And of course, these are the folks who funded the work, and I have to acknowledge them. Liang's work is, again, also critically dependent on actual material. Some very special thin films that we got from the group of Professor Bühler-Paschen in Vienna. So I'm going to start off talking a little bit about electrons and about electrons in solids. I encourage people, if they have questions, please feel free to interrupt. And then I'll talk a bit about what are called correlated materials and why they're interesting, and the copper oxides in particular. And then I'll tell you a kind of an introduction about noise and what I mean by noise. And then I'll get to sort of the scientific results. First, the somewhat unusual results that we find in the copper oxides, and these are kind of sneak preview pictures that are basically from the copper oxide work. And then our very recent results about what are called strange metals. And I'll also in the intro try and explain what I mean by strange. Scientists are not always that good at coming up with names for things. So you've got ordinary metals and you got strange metals. and then I'll conclude. So what are electrons? I think you all know this. Electrons are infinitesimal point particles, but since I can't draw infinitely small things, I'm doing what they do in the textbooks, and I'm approximating electrons as big blue spheres. And electrons are elementary particles, at least as far as we know, and they have charge -e. And we can all blame Benjamin Franklin for, he had a 50-50 chance to assign the sign convention for electrical charge, and annoyingly he guessed wrong. So that's why electrons have charge -e, and that's why current flows in the opposite direction of the actual particles. Electrons carry angular momentum, spin, that's intrinsic to the electrons. And again, a talk on what spin is a whole separate issue. But they have spin 1/2, which means they have, if you look at their angular momentum along some axis, they have h⁻/2 worth of angular momentum along a given axis. They are fermions. So what do I mean by fermions? That means that if you swap the positions of two electrons, say, then the quantum wave function describing those electrons picks up a minus sign, right? There's two kinds of particles in the world. There's in elementary particles, there's fermions and bosons. With bosons, if you swap the particles, the sign stays the same for the wave function. For electrons, the sign swaps. And this is a big deal, because this implies in general that the quantum state has to be antisymmetric, picks up a minus sign. When you exchange the full quantum numbers for any of the particles, that includes their positions. And that leads to the Pauli exclusion principle, right? So it just means that if I've got a wave function describing a couple of fermions, I can't put identical fermions in the same place, because the only way to satisfy this antisymmetry condition would be for the wave function to go to 0, which means that you can't ever find the particles at the same location. So this is a huge thing. This is an enormously consequential result. It is literally the reason why you're not falling through the floor. It is the reason why white dwarf stars don't collapse. And it's the reason for basically the stability of matter. What you find is that, if I draw some potential well and I talk about energy levels, this is some sort of cartoon of like a harmonic oscillator potential. If I start tossing electrons into that potential well, they don't all fall into the lowest energy level of the potential well. You can only stick, as shorthand for this antisymmetry condition, we like to say, and this is the way they teach it in high school chemistry, you can only stick 2 electrons per orbital or per spatial state. So there's a spin up and a spin down in this state. And then if I want to add more electrons, they have to go into higher energy levels. And that's a huge thing, right? The electrons don't all fall down to the bottom. So let's talk about what happens when I have a lot of electrons. Let's take a zillion electrons and stick them just in a box. Okay, we're going to ignore atoms for a second. We're just going to throw a zillion electrons in a box, and we're going to turn off the interactions between the electrons. We're going to ignore the fact that they're charged and repel each other. So if I have a large number of non-interacting fermions that are confined, this is something called a Fermi gas. Here's Enrico Fermi, who really figured out, in some sense, the baseline of all of this stuff. So if I look at the allowed states in the box in terms of momentum, right, in terms of wave number, I think about the particle in a box type states, what you find is what's the lowest energy state I can have? Well, the answer is that I'll start occupying states that have the smallest momentum. So that's 0, 0 in this 2-dimensional plot, or it would be like 0, 0, 0 in this 3-dimensional plot in what we call K space, momentum space. And I'll start filling up states. And then at 0 temperature, I'll have a bunch of filled states and a bunch of empty states. And there will be a sharp boundary between the filled states and the empty states. This filled states are called the Fermi sea. And the empty state, this boundary between the filled and empty states is called the Fermi surface. And that's the ground state. So what happens if I add a little bit of energy to the system? What are the low energy excitations of this collection of fermions? Well, they're called particles and holes. So here's in momentum space, here's my disk again. Here's all the filled states. And if I look at things as a function of energy, I've got uniformly filled states up to some high level called the Fermi energy. If I add a little bit more energy, I can take electrons out of the filled states and put them into the empty states. And so my excitations are called particles, right? They really are like electrons. They have all the properties of an electron, since we've turned off all the interactions. And what that means is they've got charge E or minus E if they're out here. The hole left behind acts like it has charge plus E. These things have spin 1/2. And if I do some kind of kinetic theory and worry about these things scattering off of maybe some dirt, but otherwise I've got just free particles. If you go and do that calculation, you find that the electrical resistivity in that toy model should go like a constant set by whatever the dirt is that you have, plus something proportional to T squared. And if you want to worry about thermodynamics, you can figure out what the heat capacity of this stuff is, and it goes like T at low temperatures. Okay, so this is a Fermi gas. So one of the great intellectual triumphs of 20th century physics, even though I think it's kind of unsung compared to a lot of things you hear about in the popular press, is something called Fermi liquid theory. And it was dreamed up by Lev Landau, who was one of the most brilliant physicists of the 20th century. And Fermi liquid theory is like the standard model for solids, right? It's the equivalent of the particle physics standard model for metals, right? So here's again my Fermi sphere and a particle sitting around outside this thing. Let's turn on the interactions. Landau showed that if you imagine dialing up now, we're going to turn on the electron-electron repulsion. What happens? Well, it turns out under a variety of conditions, there is a 1-to-1 correspondence between the non-interacting case and the interacting case. Now, things look a little different over here. I changed the color, but also my particle doesn't look quite the same anymore, and maybe there's some sort of disturbance around some nearby values in K-space here on the Fermi C. So what's going on here? Well, it turns out that the ground state is still a bunch of filled states in K-space. There's still a boundary, so a Fermi surface. The low energy excitations are now called quasi-particles. They're particle-like, but they don't live forever, okay? They've got a lifetime, tau, but that lifetime is such that the energy uncertainty, like h bar over tau, that's kind of the energy uncertainty, how fuzzed out in energy the particles are because they only live a finite time. That energy uncertainty is always smaller than kT, the thermal energy scale. Okay, what that means is that the quasi-particles out here are always energetically distinct from the Fermi surface. And interestingly, the resistivity in this kind of a model still goes like T squared at low temperatures. The heat capacity still goes like T. So you can see in a Fermi liquid, which describes copper or aluminum or gold, the quasi-particles still act like electrons. You can really think about charge being carried by these discrete objects that have well-defined charge. They live a long time. And so that's kind of the standard picture of metals. Now, what happens when this fails, right? So one thing, as I'm sure you've probably come to appreciate now, scientists in general, but physicists in particular, like to take models and then ask, okay, when do the underlying assumptions break down and the model falls apart? That's where the interesting things happen. So there are things that are called non-Fermi liquids, and these are very much of intellectual interest. And there are two very famous examples these days. There are others, but there are two famous examples. One is the copper oxide superconductors, and this is a phase diagram of these things. This will come up later in the talk. As you can see, there's a whole bunch of different phases labeled in this diagram of temperature versus doping, which is sort of like how many charge carriers do I have? And it's a mess. There's a lot of things going on here. Another example are so-called quantum critical strange metals, where at 0 temperature, if you dial around some parameter like magnetic field or pressure, at 0 temperature, the ground state of this system undergoes some real serious change, right? And what you find is at finite temperature above that quantum critical point, all kinds of weird stuff happens. So we'll talk more about that in a minute. When do you have, what are these? Both of those materials are examples of so-called strongly correlated materials. So you can have a metric for how correlated something is. Basically, you can do a toy calculation, turning off all the interactions, and figure out what the conductivity should look like as a function of frequency. And you can compare that to what you actually see in an experiment. And so if that ratio if the ratio of the conductivity in the experiment to the no interaction version of the calculation is 1, you have weak correlations, right? And that's the example if you have silver or copper. But if you start talking about some of these systems where a simple naive calculation tells you they should be a metal, like this lanthanum copper oxide. And instead, you find it's an insulator. So that ratio becomes basically 0. So that's really something very dramatic has happened, right? Somehow interactions have really broken the standard picture of metals there. This gets to, something that you may not have appreciated before, but I will try and convince you. Single electron physics is unreasonably good at describing the world around us, right? When you take chemistry in high school, you learn all about atomic orbitals. You learn about s, p, d orbitals, all of these things, right? And these are all solutions, approximate solutions, to the single electron hydrogen atom problem. So once you've taken a little bit of quantum mechanics and you understand that interacting problems are really hard, it should dawn on you that it should be amazing that this works, right? Because in a uranium atom, you've got 92 electrons that all repel each other, and they're in a tiny, tiny volume. They can't really avoid each other. And yet somehow the wave functions, the orbitals, the energy level structure, it really looks like almost the free electron problem, the single particle problem. So why is that? Well, and the answer really is the Pauli principle, right? Remember, I told you if you throw more electrons in there, they have to go into higher and higher kinetic energy states. And what happens in atoms, for the most part, with a few little exceptions, is if the kinetic energy grows really fast as you add more and more electrons into the system, and it grows faster than the electron-electron interaction, then the kinetic energy wins, and the interactions aren't very important. Now, the same thing happens an awful lot of the time in solids, right? So I can take a periodic potential in space, and I can solve the problem of a single electron in a periodic 1D potential, and I will get energy bands. I will get energy as a function of momentum that has, kind of an interesting shape, right? There are regions of energy where I've got a lot of energy levels. There are band gaps where I don't have any allowed electronic states at all, right? And if you want to understand the properties of a lot of ordinary materials, you can just do the single particle problem and then start filling up these bands. You just throw electrons in there. And if you completely fill up a couple of bands and that's it, and then there's a gap to the next empty states, you have either a semiconductor, if that energy gap is relatively small, or you have what's called a band insulator. So if that energy gap is 7 electron volts, you have diamond, okay? And it's very, very insulating. And you can, and similarly, if you start filling up the band and you end up somewhere, you run out of electrons, you end up in the middle of a band, you have a metal. And so, again, this is the example. The band structure looks a little more complicated for something like silicon. And so if you add a few more electrons than it needs to fill up the bands in silicon, you end up in a little bit into what's called the conduction band in silicon. You end up with these little blobs in momentum space. That's where the electrons are living, in the conduction band, right? But you can get all of this for materials like silicon, gallium arsenide, the standard metals, all of the germanium, all of these things you can understand very well without any electron-electron interactions in the problem at all, okay? If you want to get the fine details right, you have to account for them perturbatively, but you can get a lot of it without any interactions. So when does this fall apart? Well, the answer seems to be what you want to get strong correlations, strong interactions, is you want a partially filled band from comparatively localized orbitals. Okay, so like d and f orbitals. And so what you find is that the band, the energy bands, the kinetic energy doesn't vary very much with momentum. And if the kinetic energy is small, then you don't need much interaction to dominate the kinetic energy part. And so one famous example is something called a Mott insulator. If I have what's called a Mott insulator, the copper oxides are based on Mott insulators, grossly speaking. If you do simple electron counting, they should be metal. You should have the highest occupied states should be somewhere in the middle of a band that's built out of the copper d orbitals. But in practice, there's a band gap that opens up because the electrons repel each other. If you want to stick 2 electrons in the same copper d orbital, they repel each other enough that becomes very energetically expensive. And so they kind of lock into place and can't really move very well. A real concrete example of this is a cartoon from a colleague of mine at the University of Chicago who does atomic physics. where in this case, they've made basically a 2D egg carton potential, and they've stuck atoms in there. And it's the same idea. These are fermionic atoms. And if you try and stick two atoms on the same site, they repel each other because they can dial the interactions around in this atomic physics system. And so instead, even though in principle you could stick two atoms per site and these things should hop around all over the place, their repulsion is enough that they lock in place. So let me talk a little bit about strange metals. So strange metals, you may not have heard of. They're less well known than fancy superconductors. But in strange metals, basically they're strange, but they are metals in the sense that when you cool them down, they're electrically conductive. They're generally good electrical conductors. You cool them down, they become better conductors. So that's a hallmark of being a metal. But the thing that's weird about them at first glance is that the power law is wrong. Remember, I told you the power law goes like some residual resistivity due to dirt in your sample plus temperature to some power. And for a Fermi liquid, that power should be 2. But what you can see is here in one of the copper oxides and here in this material we're going to talk about later, ytterbium rhodium 2 silicon 2, there's a big region where instead of that power law being 2, the power law is 1, right? The resistivity is linear in temperature. It turns out also the heat capacity does odd things too. But so this may seem like not a big deal. I mean, okay, so the power law is 1 instead of 2. Who cares? Well, it turns out that this has, if you turn the theorists loose on this, they will tell you this has really deep ramifications. It implies that this whole picture of quasiparticles, of well-defined, charge minus E, spin a half things bopping around, that whole picture falls apart, potentially, in the strange metal case, because you just can't get linear in T resistivity from that, right? So something very peculiar is going on. And there's lots of exotic explanations for this, which I can get into if people want. I mean, again, one of the things that motivates me as an experimentalist is, okay, some of my theory colleagues concoct or formulate some very exotic sounding models for these systems. How do you ever test these ideas, right? What can you do in the lab to measure besides just the temperature dependence of the resistivity? What else can you measure to figure out what's actually going on? All right. Now, I do want to say just briefly, there's some real challenges with I do nanostructure work. In my group we make small things generally, and all the techniques for making small things were basically developed for on the kind of the condensed matter side, were developed for the computer industry for making chips. So there's very good recipes for working with silicon, germanium, semiconductors, ordinary metals. These correlated materials tend to be very complicated, right? So often they're not even grown in thin film form. Here's some hunk of stuff. It turns out this is strontium ruthenate, another oxide. And the problem is these properties of some of these materials, they change. And you can see someone's just silver epoxied a couple of wires onto this thing, right? If you mess with the chemistry of these things, you change the properties. If you mess with the strain, you change the properties. It's very challenging to get good material. If you try and pattern them to make devices, to make wires, to make loops, to make complicated structures, if you mess around with the chemistry at all, you can completely change the properties of the system, right? So that's a challenge. That's one of the main things my students have had to overcome. And also, contacts and interfaces and things have a lot of importance. So what you'd really like, of course, is, I just throw some wires on my sample and I just care about the properties of the material itself. You'd love to do experiments where the contacts don't matter, because the contacts might be hard to control. You don't want to be in a situation where every time you wire the device up, it's different. But so you have to get good at making contacts and understanding what they're doing. Now, let me tell you a little bit about the high temperature superconductors, just to introduce those before we get too far into this. So this is a very famous overused plot of the critical temperature for superconductivity as a function of year. You can see the scale it's a terrible graph because the scale is nonlinear. This is 80 years, that's 5 years. So there's a little breakdown here, you can't see it. But superconductivity was discovered in 1911 and in things like mercury and lead. And it's a state at low temperatures where the electrons act cooperatively. We now know what happens is the electrons pair up, and those pairs form a single macroscopic quantum coherent state. Lots of exotic words there. But the bottom line is that over some range of currents and magnetic fields, superconductors can conduct electricity with no resistance. And for a long time, these materials down here are called conventional superconductors. And it looked like the highest temperature you could ever get out of conventional superconductors was on the order of 30 Kelvin. And that's nice that you can make these things, and that's useful for things like magnetic resonance imaging magnets and so on. But we don't have these as house wiring. We don't have these as transmission lines going through the countryside. Well, there was a lot of excitement in the 1980s, the late 1980s, when these copper oxides were discovered, these ceramics, where suddenly the superconducting temperature gets much higher. And this has been exactly what's going on in these copper oxides, has been an open problem since 1986. And we're still working on this, right? And in the early 2000s, another family of iron-based superconductors was discovered that also seems to share some properties related to copper oxides. That's all been very exciting. But the point is, this is still a big open problem. And it turns out these copper oxides are based on these failed metals. They're based on these highly correlated things that the parent family are insulators because of interactions. Okay. What do the copper oxides look like? Well, they've got these sheets, these copper oxygen planes with other stuff in between. And basically, they're very anisotropic. All the action, for the most part, is happening in these copper oxide planes. And like I said, the mechanism for superconductivity remains unclear. And something that's even more unusual than that, we don't understand what these things are doing really in the normal state, the non-superconducting state, where they're kind of metallic, but they don't seem to be conventional metals, right? It's a very high stakes thing. There's been a long history of people really arguing with each other very passionately about this. So I was a little trepidatious, a little nervous to get into this, but I did. And I'll tell you a bit about it. So again, here's the phase diagram of these things, a phase diagram of these things from a very nice review article. So the parent compound, where you don't dope the stuff at all, the pure copper oxide, is a Mott insulator. That's over here. Turns out it's an antiferromagnet. That's what AF stands for. You add a few charge carriers in there by substituting different elements in, and you come into a region where it's kind of conductive, but there's something called the pseudo gap. I'll tell you about that in a second. If you add even more stuff, more conductivity to the system, it becomes one of these strange metals. And at the low temperature end, a lot of this stuff is cut off by superconductivity, like I was saying. It's a weird kind of superconductivity compared to lead or mercury. It's called D-wave superconductivity. So in an ordinary old school superconductor, when the electrons pair up, the wave function for that pair looks like an s orbital. There's no angular momentum, right? But in an unusual superconductor like this, they pair up with angular momentum 2, which means that the orbital, if you will, that describes the pair looks like a d orbital, right, rather than an s orbital. Very interesting. So again, I know this is probably a lot of technical detail for some people, so I apologize, but I just want to point out something funky here. So if you look at in momentum space, if you look at with the edge of the Fermi surface, if you look at the boundary between occupied and empty states, it looks because of the symmetry of the material, it's got these funky arcs to it. Okay, and it turns out that in the superconducting state, the superconductivity order parameter, the thing that tells you about the pairing, because of the D wave, it goes to 0 at the 45-degree points here, and here. But it turns out that what's funky is it starts to go to 0. It starts to have a depressed value way above before the superconductivity kicks in, right? So here's an example of some data. The details aren't particularly important, but the bottom line is when the system's superconducting, a bunch of the electronic states near that Fermi energy get eaten up, and you open up what's called a gap. That's why there's this big dip at the Fermi energy. That's what in the blue case, this is in the superconducting state. And the important thing to realize is that there's a dip that starts forming like at temperatures a factor of 2 higher than the superconducting temperature. So something weird is going on to the system way before it ever starts superconducting. This dip here is called the pseudo gap. Okay. And so what's going on in the pseudo gap? And this is one of the questions I was interested in answering, right? One possibility is that some people think is happening is that the electrons are already starting to pair up. They're not acting like independent electrons anymore. Somehow they're already starting to form pairs, but somehow we don't have superconductivity yet. So how would we ever test that idea? Okay. And I will tell you the answer is that noise can tell us something about these issues. I should also say, before my last slide before we actually talk about noise, there's a whole bunch of, like I said, there's a whole bunch of weird competing ordered states that you can find apparently in these copper oxides. There's a lot of different things going on. They're very complicated materials. These are from some scanning tunneling microscopy images where the electronic states are doing, have patterns in them that spontaneously evolve. We can talk about stripes and checkerboards and pair density waves and all kinds of stuff. Okay, so that's sort of the background intro about correlated materials, electrons and solids. That's all motivation. So now that I've been talking at you for half an hour, let's actually talk about noise. What do I mean by noise? So you're used to this idea. I think we all have an intuitive idea about what noise is, right? Noise is some kind of random sounding fluctuation of something, right? And usually when people talk about noise, it's as if it's an annoyance. And I'm going to try and convince you that it's not necessarily an annoyance. So, here is a simple, sine wave, cosine wave actually, as a function of time that I generated using MATLAB. So imagine I've got a signal that I want to measure, right? I just want to introduce the idea of thinking about these things as a function of frequency, right? So if I take this thing here, here's what would be musically a pure tone. I'm going to Fourier transform that and look at that as a function of frequency. I'm going to look at the power that's in this signal as a function of frequency. What you find is all that power is concentrated at a special frequency, which is basically the frequency your eye picks out for this cosine wave. And there's a little bit of fuzz left over from my numerical Fourier transform because I don't have a perfect cosine wave that goes on forever, right? The point is it's useful to look in the frequency domain. So what happens if I have noise? So what I've done now is I've taken that cosine wave and I've thrown in some random variations on top of it. Looks pretty ugly. Your eye might think there's still something under there. And so if we Fourier transform it, what do you see? Oh yeah, there's still a peak, right? There's still a lot of power, if you will, at a particular frequency. But the background is just bigger now. Okay. So that's the conventional idea that you have in your head of noise. It's something that's kind of interfering with a signal, right? There's many different kinds of noise in electronic measurements. Anyone who's ever tried to do anything in a lab will verify this. If you've ever tried to listen to a distant radio station, you know what I'm talking about. Some of the sources of noise are not that annoying scientist in the lab down the hall running the microwave oven. Some of them are intrinsic, they're unavoidable, right? And I'm going to talk about those in a minute. And the unavoidable intrinsic kinds of electronic noise contain really important physics. So one of these things is called Johnson-Nyquist noise or thermal noise. So if I just have a resistor and I just let it sit there at finite temperature, it turns out that the voltage across the resistor will fluctuate in time because the electrons are getting kicked just thermally. Thermal fluctuations are kicking the electrons around. So if I have the resistor just as an open circuit and I measure the voltage between the two ends, it will fluctuate and I will get fluctuations. This S sub V is the voltage noise power. So it would be units of volts squared. It's the mean square fluctuations in the voltage per unit bandwidth. So volts squared per hertz. The noise is independent in frequency out to a very high frequency scale. And similarly, if I short circuited the resistor, if I just put a perfect wire connecting the two ends of the resistor, what you'd find is that the current in that wire would fluctuate. And this G is the conductance, it's 1 over the resistance. So what you can see is the fluctuations are just directly proportional to the temperature, right? This is unavoidable. This is just thermodynamics. There's some very beautiful arguments about this. The original paper by Nyquist, and well, Johnson did the experiment. Nyquist did a theoretical explanation of this in 1928. The paper is about 2.5 pages, and it's a more clear explanation than I think you'll find in a lot of textbooks. So you can actually use this as a thermometer, right? So in the lab, we can go into the lab, we can hook a resistor up and measure the voltage across it as a function of the voltage fluctuations as a function of frequency. Now, I told you the voltage fluctuation should be independent of frequency, and this doesn't look independent of frequency. Well, that's because in the lab, the wiring has some capacitance to it. And so the resistor and the capacitor together act like a filter, and your signal drops off at high frequencies. The signal you actually detect drops off at high frequencies because of this filtering effect. But I don't know if you can see this dotted red line in here. We can fit that. We can account for that. So once you account for that, you can measure the noise as a function of temperature, and you can test this formula. And guess what? It totally works, right? The blue points are the experiment. The red line is zero adjustable parameter theory. And what you really do find is that, yes, the voltage fluctuations in a resistor really do measure the temperature, right? So that's one kind of noise, the thermal noise. And this is an equilibrium thing. Shot noise is the more informative noise in our case, right? So this is Walter Schottky, and over 100 years ago, he was worrying about vacuum tubes, and he was doing a statistical problem. He said, suppose I just have electrons. I'm not going to worry about repulsion or anything. I'm just going to say I've got electrons. They're being boiled off of a filament. In some way, they're going to end up at an anode. Somehow this is inside a vacuum tube. This is the vacuum tube equivalent of a diode. And I'm just going to say that these electrons are going through there, and there's some average arrival rate of electrons. But this electron doesn't know when the last one went, and it doesn't know when the next one's going. So these obey Poisson statistics. And you can do the statistics problem and ask, okay, so I know the average arrival rate, which means I know the average current. But sometimes the electrons are closer together and sometimes they're farther apart in time. So what do the fluctuations look like? So you can do the calculation and you find, yeah, the current has fluctuations, mean square fluctuations per unit bandwidth that are proportional to the average current. And the constant of proportionality has the actual electronic charge in there, right? And of course, if the electron arrivals are not independent, the noise could be something different. And usually what people do in actual experiments is they take what they measure, they compare it to the ideal non-interacting electron case, and the ratio is this thing called the Fano factor, okay? So how does this come about, right? What's going on here? Well, there's a way to think about it, and I hopefully you'll be able to hear this correctly. So think about rain falling on the roof of your car or your house, right? You can imagine, there's different ways the water can fall on your car. You can have the same amount of water per unit time falling on your car in different ways. You could have a few randomly spaced huge raindrops, or you could have a very fine mist. You can have the same amount of water per unit time, which is the equivalent of the current, but it can be distributed very differently. So if I have, some rare blobs coming along, the current, the rain would sound like this. Okay. Pretty loud, pretty discretely spaced events there. You can easily hear the fluctuations. Sorry, I didn't want to play that twice. So what if the droplets are smaller, but they come more frequently because I need to have the same current flowing? Well, then it's a little quieter, right? It's actually a little smoother in time. And of course, we can do the fine mist version of this, right? Where that's actually a much smoother in time, but the droplets are very tiny. All of these things have the same current. So only by listening to the fluctuations can we figure out how big are the blobs, right? How is the water arriving? So if we are able to measure the shot noise in the current, we can figure out the magnitude of the tunneling charge. We can figure the magnitude of the charge that's getting through the system. I should have revised this slide. We can figure out whether charge is coming one electron at a time or whether it's doing something different. And what this really looks like, if you look at the noise as a function of current, right? At zero current, you're back here at the Johnson-Nyquist number. You're back here at the thermal noise. But if I can have different things. So the single electron result, if you actually want to know what the shape of this curve is, it's this hyperbolic cotangent thing, where in the low current limit, the low bias limit, where you're basically in equilibrium, you're not driving the thing very hard, you get exactly this Johnson noise expression. And in the high bias limit, you get exactly this 2EI, twice the charge times the current expression, right? And so this interpolates between these very nicely. So that's this case where I've got Poisson arriving electrons. Now, if the electrons are coming perfectly regularly spaced in time for some reason, like maybe they repel each other so much that they come in lockstep, that would give me a Fano factor of 0. I'd have no noise. Or if the electrons were a continuous fluid, imagine that there are no distinct quasi-particles at all anymore. If they're just an indistinct fluid, then again, my noise would be very, very small. If they came in pairs, then my Fano factor should be 2, right? So I'm going to talk about 2 sets of experiments. I'm going to talk about experiments in the copper oxides, where we're going to try and figure out how the charges are coming in that pseudogap phase, the weird normal state in the copper oxide superconductors. And then I'm also going to talk about the strange metal case, right? Different, very closely related experiment. And we'll see some neat results. I should point out that shot noise, I'm not the first person to ever do this. There was some beautiful work done by a group in Israel and a group in France, where they were looking at a two-dimensional electronic system, where it's, if I was giving a different talk, I would have spent time on this. It's a very interesting system where the electrons in 2 dimensions, in the presence of a magnetic field, they really don't act like electrons anymore. In some very real sense, the low energy excitations of this collective system act like they've got fractional charge, right? If you do the shot noise measurement in the right way, you find a Fano factor of 1/3 in this funny geometry that is telling you it's like whatever the low energy excitations of the system are, they're fractionally charged, right? Which is very exotic. I mean, you heard about fractional charge when people talk about quarks and things like that, fundamental elementary particle things, but somehow in the solid, all the electrons acting together in the presence of this magnetic field, and you end up with excitations that act like they're fractionally charged. This is the kind of thing that gets condensed matter physics people very excited. It's very exotic. And it does make you wonder whether the fractional charges that come up in high energy physics bear some connection to this sort of thing, right? Where somehow, even though underlying things might not be fractionally charged, can you have a situation where the excitations are? Okay, so let me now actually talk about the experiment in the copper oxides. Like I said at the beginning, I couldn't have done any of this without really high quality material. That's a lesson to take away when you're doing experiments in condensed matter physics. The quality of your samples is very, very important, because disorder, imperfections can really make life very challenging to figure out what's going on. So these materials are grown by my colleagues, Ivan Bozovic and Tony Bollinger at Brookhaven National Lab. And what these are what's called tunnel junctions, okay? So they can grow with atomic precision. They've spent 20 plus years figuring out how to do this. So this is not a trivial thing, but they can grow atomically precise layers of lanthanum strontium copper oxide, right? So you're sticking some strontium in here. That's the thing that's giving you charge carriers. That's the thing that's making this stuff conductive. And what they've done is they've grown a layer of LSCO, and then they've grown a few layers, like 3 layers, 1.5 unit cells, of the undoped stuff, the parent compound, pure lanthanum copper oxide. That's the insulator. That's the exotic insulator. All right. And then they've grown more LSCO on top. So what we have is conductor, insulator, conductor. And the insulator is very thin. So you can do what's called tunneling. You can have a situation where the charge carriers, if you drive them, can tunnel, can go through the classically forbidden region, if you will, either from the bottom to the top or from the top to the bottom, but you can get current to flow this way, up and down in this picture. And what we're going to do is we're going to look at a bunch of different doping values, a bunch of different values of X here, right? So when X is 0.15, that's about as good in this material. It's about as good as the superconductivity gets at ambient pressure. TC is around 39 Kelvin. That's when it goes superconducting. Okay. Here's an actual cross-sectional electron microscopy image. And you need multi-million-dollar machines to take images like this, but they are very, very pretty. And this is the substrate, and this is open space up at the top. But you can this is the actual lattice, and you might think to yourself, well, okay, it looks pretty uniform. All you've done is Photoshop a couple of dotted lines on there. How do I know that there's actually this barrier in there? Well, it turns out you can with these very fancy microscopes, you can look at X-ray fluorescence. There's different ways to look at the elemental composition. And what you find is in that little thin layer, there's a little bit of excess lanthanum, a little bit of a deficit of strontium. That's how you know that's the barrier. Okay. So you can take these beautiful films and then you can carve them up. And this is the hard bit. How do you carve them up without ruining them? And again, they've developed processes for this. My student, Pan, went to Brookhaven and over a summer and spent a few weeks working particularly with Tony, on how to actually do this processing. So you can take your 3-layer thing, you can coat the top of it with gold, you can carve it into basically a mesa. You can put some insulating layers around it just to make sure you don't accidentally short the top to the bottom. And you can contact the top of this mesa and the top electrode and the bottom electrode separately. And now you've made a tunnel device. And here's a kind of a false color electron microscope image. If you look really closely, you can see this is a little round mesa, and it's contacted here and here by these 2 electrodes, and the bottom is contacted here and here. So you can actually do measurements on these things. So how do we do the measurement? Well, it really is not that complicated in concept. Here's the device, the gray dashed line, the gray dashed box is the device. And what we want to do is just measure the voltage across it. So you might imagine I'm just going to take an amplifier and do A minus B. I'm just going to look at the voltage difference between the 2 sides of the device. You got to be a little more careful than that because amplifiers themselves have noise. So what we do is we take 2 sets of amplifiers in parallel and we correlate them, because the idea here is if there's something really going on in the sample, both amplifiers will see it. But if it's something peculiar to just one amplifier, then when we correlate them, it'll go away, right? So, and then the rest of this stuff out here, this is just the apparatus you need to quietly apply a DC voltage to your device so that you can drive current through it, right? And you got to be careful about this. You don't want to introduce a bunch of noise with the way you're applying the DC voltage, but that's kind of a lab detail. So you can do these measurements, and some places even do this as an advanced undergrad lab for certain systems. So let me show you actual data, right? As we near we're at like the 45-minute mark in the talk. I'll show you actual data. So this is electrical resistance versus temperature of one of these copper oxide devices. And what you see is, as you cool it, it becomes more insulating, okay? That's because you got that insulating spacer in there. And then when you get to really low temperatures, this is in Kelvin, it really becomes a lot more insulating. And then I can also look at what's called the differential conductance. I can look at basically the slope of the IV curve. And what you find is that it's always got some curvature to it. At low temperatures, this real dip starts forming at low voltages. So this is really a sign that what's going on is that it turns out superconductivity is kicking in. And this is that dip I was telling you about, where you're kind of eating up all the ordinary electronic states that are available. You can kind of replot this data in a normalized way, and you can see, yeah, below, at 50K, when the thing's not superconducting, this is pretty flat. But as you cool down, it starts really, really getting, cuspy. This is an almost optimally doped case. I should point out this differential conductance is a function of voltage. If you had just a resistor, this would just be a perfectly horizontal line. Okay, because a perfect resistor, the IV curve is just a line. So if you take its derivative, you just get a constant. Okay, so this just tells you this is a nonlinear thing. This is not a simple resistor anymore. That's fine. So now I'm going to show you sort of like a flip book, where we're going to really see what happens as we lower the temperature. Okay, so I've got a few different things plotted here. The panels to really pay attention to are the leftmost panel and the rightmost panel. So this is dVdI, it's 1 over dIdV, as a function of the current that I'm driving, right? And again, if this was just a resistor, this would be a line, okay? And what we have on the right side, this is the current noise. And as a function of the applied voltage, here's the current noise as a function of the applied current. These two plots are really the same thing. It's just current versus voltage. The red line here is what you should expect if you have this resistance versus current, if you just have single electrons, right? So in some sense, the red curve is the theory curve, right? If you just have single electrons. Here we are at 105 Kelvin, pretty toasty warm on the scale, even though it's much colder than room temperature, it's pretty toasty warm for this material. So let's cool down and see what happens, right? Oh, I should point out at zero driving, when the thing's totally in equilibrium, the noise level here is exactly what you expect. It's exactly the thermal noise, the Johnson-Nyquist noise, that's all fine. So let's cool down. And as we start cooling, you can see this thing gets more and more nonlinear, more non-ohmic. And notice, even here we are at 65 K, quite a bit, 25 degrees or so above the superconducting transition. And already, if you look closely, these blue data points are lying above the red line. There's more noise than you'd expect for just single electrons tunneling by themselves. Okay. As you cool down, this gets more dramatic. Here we are getting close to the superconducting temperature, and now you can really see there's quite some separation here. Okay. Right around TC, it's more pronounced. Now, when you get well below TC, complicated things happen, and you get really wild noise going on. I don't want to get into the details of this because it's a little bit beside the point. That sort of thing actually can happen in ordinary superconducting tunnel junctions as well. It's a complicated multi-electron thing that can go on. But the bottom line is that things get very complicated, right? But the things get there's lots of deviations from single particle expectations way above TC. So we can plot this in a different way, right? What I'm plotting here is called something we defined called the noise ratio. It's basically the measured noise divided by the single particle tunneling expectation. And so here we are at 100 Kelvin. Pretty much this ratio is 1, maybe a little bit of a deviation. But as you start cooling down, again, you can see it starts to deviate from 1, pretty warm, right? And then, again, we're well above TC, but this deviates a lot, right? And then, of course, like I said, wild things happen well below TC. So the noise clearly exceeds the single electron case. What does that mean? Well, it means that sometimes more than one electron is going through at a time. Okay. This more surprising thing, actually, in some sense, is that this is happening at pretty high energies compared to the energy scale for superconductivity, it turns out. That was a surprise to us. We did not expect that. So let me show you how carefully we looked at this. This is a pretty exotic result. We wanted to look at 4 different compositions, 4 different values of X, 4 different kinds of 4 different compositions of the superconductor. So here's X equals 0.15, 0.14, 0.12, 0.1. And the top row, this is that noise ratio as a function of voltage for everything below the superconducting temperature. But the bottom row is for everything above the superconducting temperature. And you can see there's a lot of stuff above this light blue surface for all of these things. And it extends out to pretty high voltages. That's weird. And we were so interested in this, we did this in a whole second set of samples. So my student did a lot of heroic experimentation and data processing. But here, just to see it's reproducible, here's a whole second set of all 4 compositions. And this is still persistently true. Right. So, we can do a toy model calculation. We can say, gee, maybe some fraction of the current, maybe the noise is high because some fraction of the current's being carried by pairs, even in the normal state. So can we figure that out? Well, you can do a model. I'm not sure I would, stick my hand in a fire over this model, but it's a model. We know what the single electron thing should do. We can play games and say, well, imagine that a tiny fraction Z, or a small fraction Z, of the current is actually carried by pairs. Within that model, you expect something that looks kind of like this. And you can do algebra, and you can basically solve for Z, right, in terms of things you measure. So we know the voltage, we know the temperature. we know the noise we measure, we know the noise we should see for the single electron case. So we know everything on the right-hand side experimentally, right? So we should be able to back out Z. Now you got to be careful when you do that, because if you go in the zero bias limit, if you go down to very low voltages, the denominator of this thing blows up. So or rather the denominator goes to zero, excuse me. So you can't really do this calculation and have everything work because you're sort of dividing by zero. And that's fine, because we all know, like I said at the very beginning, if you're in equilibrium, if you're not driving the thing at all you should get is the Johnson-Nyquist noise, right? And the Johnson-Nyquist noise doesn't care if there are pairs. It doesn't care about anything except the resistance. So this is fine. So you just have to be careful not to trust this number that you pull out of your data when your voltages get low. So that's why in these plots here, I've done a color map of that Z number. And the color scale ranges from 0.5 to 0. And these shaded regions are where you really shouldn't trust that Z number very much because the voltage scale is small. But what you find is that the red curve is what you should see for a conventional superconductor. That's the boundary of the superconductivity, basically. And what you find is there's a lot of blue outside that boundary. There's a lot of indication of pairing outside that boundary at high temperatures, right? And also at voltages that are big. And this was, again, very surprising and very interesting to us. I think it tells you that the pairing of the electrons, the electrons not acting like individual electrons anymore, the pairing is somehow more robust than superconductivity, right? When you go above TC in one of these materials, superconductivity dies, but the pairs don't, it doesn't die because the pairs fall apart, which is what happens in something like lead. It dies because somehow the coherence, the ballet dance of all the pairs together stops. Now, a control experiment, you could do the same experiment in a conventional superconductor, right? So we did the same kind of measurements in niobium, a commercially purchased niobium junction. And you can see in that plot, yeah, I mean, we couldn't get that cold for various reasons, but basically, it doesn't look like those other things at all, right? You basically never see that enhanced noise at high biases or at high temperatures in the conventional superconductor case. So that was pretty cool. Now let me tell you about our most recent result, right? In maybe the last, I'll try and do this in maybe 15 minutes to allow some time for questions. So let's talk about strange metals. Okay, hopefully you've already been convinced that shot noise can tell you interesting things. Let me show you maybe even more dramatic version of this. So we're going to look at ytterbium rhodium 2 silicon 2. This is a funky intermetallic compound that you probably have never encountered unless you do research in this exact area. It's one of a family of these things. And it is what's called a quantum critical strange metal. So it's part of a family of materials called heavy fermion materials. These are materials where they contain F electrons. That's what the ytterbium is, a rare earth. It's got the F electrons in there, right? And these F electrons end up talking to the conduction electrons, and you end up with very flat, comparatively flat bands. And this is another way of saying that the effective mass, the charge carriers in the system act like they're really heavy, like hundreds of times more massive than free electrons. That just means that if you vary their momentum, their kinetic energy doesn't go up very much. Okay. And this material in particular, at low magnetic fields, the magnetic moment of those F electrons is ordered antiferromagnetically. They form a pattern, up, down, up, down, up, down, up, down. Okay. But it's a Fermi liquid. So the resistivity goes like T squared. Okay. At high values of magnetic field, you kill this antiferromagnetism, but the resistivity also goes like T squared. So you have a transition from a Fermi liquid to a different Fermi liquid. Okay. But above this transition point, the resistivity goes like T. And it's unclear what that means. It seems like the electrons are forming some big, complicated, highly entangled soup. At least that's the idea. And it's just not clear how these things, why you're getting rho going like T here. I should point out, I showed this thing spreading out in magnetic field as you go up in temperature. all of this excitement is happening below about 0.3 of a degree above absolute zero. So by the time you're up at a couple of Kelvin, where we start doing our measurements, the whole region of magnetic field is this strange metal region in this material, okay? So again, our ability to do this experiment depends critically on the availability of material. And Professor Bühler-Paschen in Vienna is basically the only group in the world, the only group in the world that's figured out how to grow nice films of this stuff, as opposed to, you know, single crystals that are kind of bulky objects, right? So she can grow very, very clean, pretty looking thin films of this stuff. So now that you have the thin films, you can pattern them, okay? Now we're not gonna make tunnel junctions this time. Instead, we're gonna make little wires. So a little bit different than before. And again, my student, Liang, spent a lot of time figuring out how to do this without ruining the material. So, you know, you can put down basically a protective coating of the gold is going to eventually be our contacts, but you've got some chrome on top just as a mask. You can have a chrome strip here. And now you're going to throw this whole thing in an etching machine where you can eat the ytterbium rhodium 2 silicon 2, but nothing else. And then you can strip off the chromium by dipping this whole thing in warm hydrochloric acid, which again, that was an interesting way to figure that out. But in the end, you end up with a device that is a little snippet of wire, right? So if we hear, this looks a little torn up because that's where the leads were bonded on. But if you zoom in, here's that little snippet of wire between two big pads, okay? And how do we know we didn't ruin the material? Well, we can compare the properties of this device, which is basically in red here as a function of temperature. This is resistance versus temperature. We can compare it with an unpatterned film. And what you find is that if you normalize everything to say 100 Kelvin, they look basically the same. And in fact, you can see at low temperatures, it's linear in T, okay, as the strange metal is supposed to be. You can look at, probably a better test is you can look at the resistance as a function of magnetic field. I'm actually not sure why this has the shape it does. But again, you can compare the nanowire device to the unpatterned device, and you see that basically nothing has changed by the patterning. So that's how you know a couple of things. That's how you know that the resistance you're measuring is really dominated by the wire, not by the pads. And it's also how you know you haven't ruined the material by patterning it. Okay, so we've got a wire. What do I expect to see in terms of the noise in a wire? It's different than a tunnel junction. So fortunately, this has all been worked out. There's different regimes you can be in, okay? But this was all worked out, 30 years ago on the theory side and tested and demonstrated on the experimental side. John Martinez is actually a tremendous experimentalist who has been basically founded Google's quantum computing effort. Michel Devereux is a fantastic experimentalist who is at Yale doing a bunch of quantum computing stuff. So folks have done very well out of this. So what do you expect to see, right? So this is the Fano factor. It's the noise divided by the Poisson result for a wire, okay? So if the wire is short compared to the electron-electron scattering length, basically the distance scale over which the electrons really bounce off each other, then and transfer energy amongst themselves, then you get you're supposed to get a Fano factor in this case, in the wire case, of 1/3. This has nothing to do with fractional charge. This is just what happens when you worry about scattering off of dirt in a little diffusive system with no energy transfer between the electrons, right? Now, if you let the electrons, if the wire is longer, so the electrons can exchange energy with each other, you can actually work it out that the Fano factor goes up, and it's supposed to be √3/4, which is about 0.433 for those who actually care about the number. And one way to think about that is that there's some effective electron temperature inside the wire where the electrons have shared energy amongst themselves. And that gives you an elevated noise, okay? Now, if the wire is too long, then the electrons can lose their energy to the vibrations of the atoms. And that's called electron phonon scattering. And so what happens is that if the wire is too long, the noise is completely suppressed. This is why you don't see shot noise in the wiring in your house, in macroscopic wires. It's because you're looking at everything on length scales big compared to the electron phonon scattering length. And at room temperature, electron phonon scattering is also very, very important. Okay, so this is the expectation. And this is in fact, basically what you see if you work with a normal metal like gold. All right. So what do you see in one of these constrictions? You don't see this. Okay. In the ytterbium rhodium 2 silicon 2, here we are at 10 Kelvin. Here's a bunch of theory curves for √3/4 Fano factor. Here's the 1/3 Fano factor. Here's a couple of other Fano factor values, and here's the data. The noise is way the stuff is quiet. All right. These wires, unlike the copper oxide superconductor case where the noise was enhanced, here the noise is suppressed well below what you'd expect for single electrons. That's weird. You can, if I cool down, what happens? Well, turns out the noise goes up a little bit. So that was 7 Kelvin. This is 5 Kelvin. This is, sorry, Zoom was being a little weird there. This is 3 Kelvin. But the noise is always way below what you'd expect for ordinary electron-like quasiparticles. Now, you might ask, maybe this is just something weird about our measurement setup, right? So let's do the control experiment. Here's a wire made out of gold. Same setup, very similar dimensions. Here's the resistance as a function of temperature for the gold wire. Hey, it looks quadratic at low temperatures, which it's supposed to. Resistance is actually rather similar. What happens in that system? Well, in that system, at 3 Kelvin, the Fano factor is about 1/3. Okay, and that's basically what you'd sort of expect. Now, in this case, as I warm up, the Fano factor does go down a little. It goes down a little because in gold, you kind of expect the phonons to be important. You expect, by the time you get up to 10 Kelvin, you expect scattering off of the lattice and energy loss from the electrons to the lattice to matter, to be detectable. Right. So let's put all these things together in here. This is a, well, here's the ytterbium rhodium 2 silicon case. Here again is √3/4 and 1/3, and here's all the data with error bars for the ytterbium rhodium 2 silicon 2. It's all the way down here. For gold, it starts out close to 1/3 and goes down a little bit. Now, you might wonder, maybe the phonons are killing maybe my phonon story from the gold is being reproduced here in the ytterbium rhodium 2 silicon 2. Maybe it's phonons. Maybe it's the lattice that's squishing everything. We don't think so. You can model this, right? You can actually figure these things out. There's ways to actually do a real calculation. I can go over the details if people want. But what really matters is this gamma. This is basically the rate at which energy gets lost to the lattice. And you can do all this calculations and play games with what you think that coupling constant is. And the bottom line is, if you want to get the noise squished this much, you have to assume that this gamma thing is 68 times higher in ytterbium rhodium 2 silicon 2 than in gold. And there is zero evidence in other measurements for that at all. If anything, you actually expect phonons to matter less in ytterbium rhodium 2 silicon 2. There's something called the Debye temperature, which the higher the Debye temperature, that's basically tells you how stiff the system is. And it tells you, you don't have to get as cold to ignore phonons. So for gold, the Debye temperature is about 170 Kelvin. For ytterbium rhodium 2 silicon 2, it's about 380 Kelvin, more than twice as high. So phonons really aren't supposed to be important in this material, and no other measurements show phonons doing anything in this system. So it does not seem reasonable that our quietness is due to phonons. So what do we think is going on, right? Here's the kind of the cartoon. Here, again, here's Fano factor versus temperature. Up here is that √3/4, and the picture there is I've got quasi-particles scattering off of each other more often than they scatter off the dirt, and the dirt is represented by these dark brown dots, okay? In the gold, and then here's the 1/3 Fano factor. That's the case where the scattering off the dirt is the dominant thing. But in both of these cases, the current is carried by these well-defined objects, these quasi-particles. The current is a function of time. You can basically look at the discrete arrivals of the particles, and that's what gives you the noise, right? That's what gives you the shot noise. So what's going on here? Well, it kind of looks like the current, there's, the stuff's very conductive, but it kind of looks like the current is not carried by discrete excitations. It's carried by somehow this soup, this highly entangled, complicated, many body interacting thing, right? That doesn't, that according to some theorists lacks these quasi-particles entirely, right? So there's a kind of a background fuzz of stuff that's carrying the current. And it's very interesting to think about these things, right? You just can't think about individuals anymore. Somehow the crowd is everything, if you want to have an analogy for people. So we're pretty excited about this result. That's why we just submitted it for publication. There's a more technical way to think about this that I'll go over very briefly. Okay. In the Fermi liquid, the way you really get the 1/3 and the √3/4 is you actually have to think about what the distribution function of the electrons is doing as a function of energy. And so the source and the drain, you've got filled states and empty states, and they're offset in energy by the voltage you apply with your battery, right? And if to get the 1/3 result, if you basically ask what's happening in the middle of the wire, you have this funky two-step thing where the distribution function is non-thermal and complicated looking. If you allow the electrons to talk to themselves, you end up with an elevated electron temperature, and the distribution function looks more like √3/4. Right, sorry, the Fano factor looks more like √3/4. In the strange metal case, the problem is that this whole Fermi liquid picture is weird, right? It does not have a crisp boundary anymore between the filled states and the empty states. It's just fuzzy. That fuzziness has to do with the interaction effects and the entanglement and the many body correlations. So if you try to write this down in terms of like individual electronic states, it looks like kind of a mess. And the bottom line is that if those many body effects are strong all the time, the distribution function looks like a mess even in the middle. And so it does not look like the result from the independent electron picture. So that's the idea. That's the idea. I mean, I think what's really interesting to me is that there is not a good theory calculation yet in the literature anywhere for what you should expect to see in that measurement. It's always a little dangerous when you're an experimentalist and you're doing work where there is not a prediction, right? It's exploratory. That can be hard to publish sometimes, but it's a lot of fun. So let me give you some conclusions, and then I'm happy to answer some questions. I hope I've given you a couple of examples about how in correlated materials, when we can't ignore the electron-electron interaction anymore, the electrons can collectively act in ways that are quite surprising. Looking at things in small structures is kind of an interesting niche, an interesting way to examine these correlated materials. The shot noise provides a comparatively direct quantitative way to look at what's going on. In the cuprates, in the copper oxide superconductors, it really looks like we get pairing above TC and at high energies, which is interesting, right? And our initial measurements in this strange metal show really suppressed noise, which suggests that quasi-particles really might not be a thing. Maybe the theorists are right. Maybe this is evidence that argues in favor of the idea that well-defined electron-like objects don't really exist anymore. I mean, obviously at high energies they do. If you bang on this thing with ultraviolet light, you'll still kick out whole electrons. But in their natural state at low energies, just letting the electrons talk to each other, they somehow lose their identity. So there's a bunch of open questions, right? Like I said, in the copper oxides, you can look at other parts of the phase diagram. We have experiments where we're trying to do this. In the strange metal case, like I said a minute ago, there is no theory for this right now. So I'm hopeful that theorists will get excited about this and try and work on this problem. And one of the big questions actually is, how universal is this response? Okay, so we measured this suppressed noise in one particular material. Now, these strange metals, there's a whole class of these. in fact, there's multiple classes of these that are where the origin of the quantum strangeness is different microscopically in each one, but the linear in T resistivity is still there. So how universal is this noise thing? So we're trying to work on a different set of materials also to test that as well. But the bottom line is there's still an awful lot to do, which is good. It's good to still have things to explore. So with that, again, thank you very much for your attention. I want to acknowledge the folks who helped out with this work and the people who paid for it, and I'd be happy to take questions.
Thank you very much, Dr. Natelson, for your lecture. We will now move on to the question and answer session. For our Zoom audience, we remind you that you can send your questions to Dr. Natelson by sending a direct message to the person named in Plex's Q&A. For our audience in person at the Congress Center, you will be informed when you can ask your question directly to Dr. Natelson. For those of you in the audience who want to make a question to Dr. Natelson, we ask you to please come close to the camera so Dr. Natelson can see you while you make your question.
I know it was a lot, and I know that was a long time to be listening to me.
There's a question over here.
Okay.
Professor, can you stand up, please?
Hi, Dr. Natelson. Thank you so much for the lecture.
Mm-hmm.
And well, I have a question of well, we're dealing with subatomic particles such as electrons, right? We often see on the equations that it appears to be, well, they all working along with the voltage and the current and all the, well, the way the dynamic of the particle deals with. But once the H, the parameter of the quantum realm appears, how much of the information that we can measure from the movement, well, the dynamic of the particles, we lose once we do the experiments, or how much we can take from that information?
So that's a good question. Let me repeat it and make sure I understand what you're asking. So that I believe you're asking, how in the act of doing the measurements, right? We're trying to infer information about this highly quantum mechanical system, and so H bar comes into the problem, and yet we're doing these measurements with these fairly gross classical things like the voltage and the current. And so the question is how are we able to draw, how much can we draw conclusions about the kind of the quantum mechanics going on underneath? Is that basically the question?
Yeah, exactly.
Yeah. No, it's really good. So the honest answer is that people have spent a long time thinking about how to connect experimentally measurable parameters where in the end you've got a voltmeter or you've got a lock-in amplifier or something, a current amplifier, with what's going on down underneath, right? And this kind of layers of models that connect from one to the other. And if you really want to see, so we're highly reliant on models that go from the microscopic to what you actually measure. I will say, calculating, going from basic theory of very quantum mechanical things and ending up with resistivity or I versus V. For some systems, this is very hard, right? So I mean, this is exactly a good thing to worry about. That's why, why isn't there a theory in these strange metals of what should the current look like? What should the noise look like? The answer is that people don't have a great way yet to connect their ideas about these strange metals to things you can measure. They can make qualitative statements, but they don't have a really, it turns out basically electronic transport in particular is tough, because not only are you trying to connect to some macroscopic measurement, but really when you drive something out of equilibrium, if you want to have a solvable model, you got to make a lot of assumptions. And so it is really tough. I mean, I think the quantum computing community, the quantum information community really struggles with this, right? Because the kinds of the kinds of measurements you can do, you want to be able to have your system do all of its, if you want to build a quantum computer, you want to have your system do all these interesting quantum operations and have very, superpositions and all kinds of quantum mechanical stuff going on. But at the end, you measure something, and you somehow have to connect the result of that measurement to the deep underpinnings about what's happening. And like, I don't have a general answer for you. This is a huge challenge in this business, and the fact is that we're kind of relying on many years of theoretical analysis and to make that connection between the microscopic and the macroscopic.
Thank you so much.
Mm-hmm.
We've got another question.
Sure.
Thank you very much, Dr. Douglas. Speaking about the material, I don't remember. I don't know if I remember exactly the composition. Ytterbium, strontium chloride.
No, so it was the superconductor was lanthanum, strontium, copper oxide.
The one of the quantum tunnel charge.
Right.
Okay.
So,
have you able to determine the Bohr radius of the material,
the Bohr radius. Well, okay. So, I mean, I think that the properties of the individual atoms are well known, right? Effectively the sizes of the atoms are well known. If you mean so in that material, when you dope it, when you stick in strontium to replace a lanthanum, you're introducing a hole, right? So now you're creating this positive, you're creating a lack of an electron. You've got this positively charged hole, and you can ask how far, if you think about at low temperatures, that hole is sort of bound to that strontium atom, and so you can talk about a Bohr radius for that. And that's on the order of, it's pretty small. It's on the order, I want to say it's on the order of about 2 nanometers. So it's bigger than an atom, but it's not much bigger than an atom. So in solids, if I take a phosphorus atom and stick it in silicon, I'm adding an electron to this thing. So I'll have basically an extra electron, and at 0 temperature, it'll be bound to this phosphorus ion. And it'll look like, kind of like in a textbook, they'll draw a cartoon where it'll be like a big puffy thing that'll look like kind of like an s orbital, and it'll have an effective Bohr radius in that case, again, of a few nanometers, right? So yeah, I mean, I think really knowing microscopically what the electronic states looks like is a challenge. There are theory techniques that can give you that information. And then when people do experimentally, you can do scanning tunneling microscopy, where you can basically image what the electrons are doing on sort of subatomic distance scales, and you can see how puffy these things look, right? So that's how the numbers I just told you are kind of that's where they come from. You can actually go and you can do a tunneling experiment with a tip, and you can actually see, oh look, there, if I look at around a strontium atom in a film of this stuff, how is the charge distributed? And you can say, oh, it's kind of a puffy thing, and it's kind of on the order of a few atoms across.
Okay, the answer was much more complicated than I expected. And how much, or what is the thickness of that thin layer?
So in the copper oxides, the total thickness of the films, like the 3 layers all together, was about 100 nanometers.
But just the material and in the center, the
material in the center, about 2 nanometers.
Okay.
It's really small.
I guess what was the technique? Molecular beam epitaxy?
Yep, molecular beam epitaxy. So this is, for those who don't know, this is basically, so there's different ways to grow thin films, and you can basically evaporate metals. There's different ways to do this. And so the way they make thin metal coatings all the time is you can just sublime a metal or evaporate a metal and just have it, you have the metal atoms land on your target and they'll just grow. Epitaxy is special because the atoms have to have enough, they have to stick, but they have to have enough freedom to move around that they find their happy spots. So you get single crystal alignment and instead of just some amorphous mess. And so these folks at Brookhaven have figured out how, exactly the right way in a very fancy, intimidating looking vacuum chamber to grow these oxide films, basically one atomic layer at a time, and have the structure be super clean. It's really impressive.
Okay, sounds impressive.
Once again, we thank Dr. Nelson for his participation in the International Symposium on Physics. We would also like to take this opportunity to thank our sponsors, without whom this event will not be possible: Ternium, Climate, AI, and HEV. Thank you very much for your presence, and see you in a few moments for a roundtable, which will start at 11:30 and at Congress Center. This roundtable will feature Anthony Leggett, Douglas Natelson, Daniel Oblak, and David Hughes. Thank you so much.
Doctor, we will wait for you in the other Zoom link. I don't know if you have it.
Oh, okay. Yeah, let me sign out from here and I will go find the other Zoom link. I definitely have it.
Okay, thank you.